So I want to take a look at one of the homework problems on linear programming. So it's actually the very first one on page 167, number 21. Someone asked about it in class, and I looked at it really quickly, and I thought that maybe part of the issue going on why they weren't getting the right answer was that part of the units was in quarts and parts was in gallons. But I read it closer, and it turns out that actually isn't relevant to the problem. So I thought I would go ahead and actually do this problem for you guys. So let's take a look and see what it looks like. Alright, so here's the question. It says a juice company makes two kinds of juice, orangeade and berry fruity. So 1 gallon of orangeade is made by mixing 2.5 quarts of orange juice and 1.5 quarts of raspberry juice, while 1 gallon of berry fruity is made by mixing 3 quarts of raspberry juice and 1 quart of orange juice. A profit of 50 cents is made on every gallon of orangeade sold, and a profit of 40 cents is made on every gallon of berry fruity sold. If the company has 150 gallons of raspberry juice and 125 gallons of orange juice on hand, how many gallons of each type of juice should be made to maximize the profit? So, alright, so the first thing to notice here is this very last sentence. It says how many gallons of each type of juice should be made to maximize the profit. So right away, we know what our objective is. So our objective here is our objective function is going to be something for profit, and we're trying to maximize it. We also know what the variables need to be. So the variables are going to be how much of each type of juice. Now I think part of the confusion in this problem is, what do they mean when they say juice? Are they talking about the orange juice and raspberry juice, or are they talking about the orangeade and the berry fruity? And it turns out it's the latter. They're talking about the orangeade and the berry fruity. Because, well, first of all, they say each type of juice should be made. So what you're making is actually the orangeade and the berry fruity, and you're making it with the ingredients. The ingredients are the orange juice and the raspberry juice. So that's what our main variables are going to be. So let's go ahead and actually get those variables down. So J is going to be the amount of orangeade that we're going to make, and it's also important to say what your units are. So our units in this case are going to be gallons. So that's going to be our first variable. Remember, in the linear program we need at least two variables, so our second variable, I'll call it B. So it'll be the amount of berry fruity that we made, and the units for that will also be in gallons. So at this stage we're ready for our objective function. So our objective is to maximize the profit, and our formula for profit, which I'm going to call P here. So our formula for profit, let's look over here. We know that we make 50 cents for every gallon of orangeade, that is really hard to say. So we're going to that by J. So for every J, we're getting 0.5, half a dollar, plus we also make our profit off of the raspberry fruities that we make. So, sorry about that. So I converted the 0.5 into 1/2, just because I like fractions. I don't really like decimals. So now let's go ahead and go on to the berry fruity. So it's 0.4 of a dollar. So 40 cents is made on every gallon of berry fruity. So that's going to be 0.4 times B. But again, I'm not a big decimal fan, so 0.4 in fractions is 4/10, which I'm going to go ahead and reduce to 2/5. So now we've got our objective function. Here's our objective function. We're for profit, P equals half J plus 2/5 B, and we're trying to maximize that. J, here's our variables. J is the amount of orangeade in gallons. B is the amount of berry fruity that we're going to make in gallons. All right, but we still need the constraints. So what's going on with the constraints? So let me actually shrink down that part of it over there, put it on the side, and our constraints are we only have so many ingredients on hand, right? Otherwise we could just make tons of orangeade and tons of berry fruity and make trillions and trillions of dollars, but unfortunately we're limited by our amount of ingredients. So let's take a look at the orange juice first. So if you think about it for orange juice, let's see what we know about the orange juice. So it says right here that orangeade is made by mixing 2.5 quarts of orange juice. So for every gallon of orangeade we made, we need this much orange juice. But at the same time, so I'm going to represent as 2.5 times J, right? For every J, that's 2.5 quarts of orange juice we need. But at the same time, it says that we need 1 quart of orange juice for every berry fruity we make. So if we make 1 berry fruity, that's 1 gallon of orange juice we need. If we make 2 berry fruities, that's 2 things of orange juice. 3 berry fruities. So same deal. We're going to multiply these together. Then we have to add up the amount of orange juice we need from the orangeade and the amount of orange juice that we need from the berry fruity. And we put those together, that's the total amount of orange juice that we're going to use. However, we're limited by the amount of orange juice because we only have 125 gallons of orange juice on hand. So therefore, this number, this formula, which is giving us how much orange juice we're using, has to be less than or equal to 125. Now, again, I'm not a big fan of decimals, so I'm going to convert the 2.5 into fraction form. That's 5/2. But I'm also not a big fan of fractions if it can be avoided, and I can get rid of this fraction just by multiplying everything by 2. So I'm going to do that. I'm just going to multiply every single thing by 2. So when we do that, here the 2's will cancel, you get a 5, 2 times 1 is 2, and 125 times 2, that's 250. So I'm just making everything be nice whole numbers because we can. Alright, so that's our constraint based on the amount of orange juice we have. But there's also a constraint based on the amount of raspberry juice we have. So let's take a look and see what we got going on there. So for the raspberry juice, we know that for every orangeade we make, we need 1.5 quarts of raspberry juice. That's for every single orangeade. So if I were to make 10 things of orangeade, that would be 15 quarts of the juice. So in other words, we have to do 1.5 times J. But that's just from the orangeade. Now we have to actually look at the berry fruity. So if we look at the berry fruity, it says the berry fruity takes 3 quarts of raspberry juice for every single gallon of berry fruity we make. So I have to do 3 times B. And I add these two together, right? So this is the amount of raspberry juice that's coming from the orangeade. This is the amount of raspberry juice that's coming from the berry fruity. So I add those together. That's going to give me the total amount of raspberry juice I need, but I'm limited to 150 gallons of raspberry juice. So that has to be less than or equal to 150. So at this stage, we've got 2 constraints, but it turns out there's more. So the implicit constraint is that I can't make a negative amount of orangeade, and I can't make a negative amount of berry fruity. So basically, we're restricting ourselves. Oh yeah, let me go ahead and change this to fractions while I'm at it. So 1.5 is 3/2, and again, we'll just do the multiply by 2 trick. So multiply everything by 2, so here the 2's are going to cancel, and this give you 3, 6, and 300. So, alright, yeah, so now we got a nice whole number. So now we've got our 2 constraints, and the 2 other constraints which are sort of implicit in this problem is that the J has to be bigger than or equal to 0, and the B has to be bigger than or equal to 0. So really, all we're looking at is the first quadrant. Alright, so just to kind of recap here, so what we're looking at now is we have our objective function, and we're trying to maximize this. We've got, in fact, 4 constraints. This one, and these 2. And we've got our variables, J and B, so we're all set to go. So at this stage, I think we're ready to do the graph. So I'm going to jump to GeoGebra for that. Actually, I had a quick change of heart. Before we go to GeoGebra, these numbers are small enough we can actually do it by hand. So let's go ahead and actually see what our constraints and so forth look like if we do it manually. So I'm just writing up here our objective function so we don't forget, 1/2 J plus 2/5 B. And we've got our orange juice constraint, which I'm going to do in orange, of course. So it's 5J plus 2B is less than or equal to 250. And then we've got our raspberry juice constraint, which of course I will do in purple. So that is 3J plus 6B less than or equal to 300. But, you know, while I'm at it, let's go ahead and simplify that. This is all multiples of 3. So if I just go ahead and divide everything by 3, that'll make life a little bit easier. So here, this will cancel, this will become 2, that'll be 100, so it looks like that. Probably should have reduced it earlier, but okay, well there we go. Now we're actually ready to make our graph right here. So just a reminder, so our horizontal axis, that's going to be our J, which is our orangeade, and then the vertical axis, normally Y, but we're using that for our berry fruity. So let's go ahead and look at what this as a line is. So really it's an inequality, but let's just do the boundary of the inequality first. So just the edge part, so as if it was an equal sign. So if we have 5J plus 2B is equal to 250, so let's find the J-intercept, what we normally call the X-intercept, but in this case it's the J for the orangeade. So remember the method is you just sort of imagine like this isn't here, right? Because wherever it crosses, that means the B component, or the Y component usually, is going to be 0. We don't know how much across to go on the J, but we didn't go up and down at all, so the B must be 0. So if the B is 0, 2 times 0 is 0, so it's just like this is gone. So just imagine if it actually just says 5J equals 250. So if you take 5j equal to 250 and divide both sides by 5, then that means j has to be 50. So, boom, we now know the j-intercept for that line. And now let's also do the b-intercept, what's normally called the y-intercept. So we don't know how much up and down to go yet, but we know the right and left part, the j part, must be 0. So you plug in j to equal 0, which is basically what we sometimes as teachers call the finger method. You put your finger over this and just look at 2b equal 250. So if 2b equals 250, then divide both sides by 2. 250 divided by 2 is 125. So we now have the two intercepts of the axis. So here on the b-axis it hits at 125. Here on the j-axis it hits at 150. We know this is a straight line because there's no exponents. So as an equality, in other words, the boundary of our region here, we can just stick that on. And we know it's going to shade down. And the reason we know it's going to shade down is we do our little origin technique. So the origin technique is we consider whether the origin, which is 0, 0, is going to be in the shaded region or not. So if you plug in 0, 0, 5 times 0, 0, plus 2 times 12, this whole side is going to be 0. And is it true for the inequality that 0 is less than or equal to 250? It sure is. So that means the origin, 0, 0, is in the shaded region. So it must be shaded down and not shaded up. Alright, so that's the orange juice constraint. Now let's do the raspberry juice constraint. So we'll do the same kind of thing. If we want to find the j-intercept, what we normally think of as the x-intercept on the horizontal axis, we cover up the 2b part because we're plugging in b to be 0. So that means j equals 100. It's not really less than or equal to now because we're looking at the boundary, right? We're just looking at the line part of it. So if j equals 100 for the intercept, we'll mark that on right there. And now we got to find the b-intercept. So this time we imagine like the j isn't there. The j is 0, so it says 2b equals 100. So if 2b equals 100, that means b equals 50, so we put that on there. So those are intercepts. We just sketch the line like so. And now let's think about the shading. Again, same deal. If you plug in 0, 0, 0 is in fact less than 100, so the shading must contain the origin, so in fact we need to shade down. So you can sort of see what's going on. And don't forget, we're trapped in the first quadrant because the j has to be positive. That means we're only looking things on the right side of B. But at the same time, the berry fruity has to be positive, so we're only looking at things above the j-axis. So we're in the first quadrant. It's got to be both in the orange shaded region and the purple shaded region. So it looks like we're looking at this quadrilateral right here. So that means we just have to figure out what the coordinates of this point are, and we'll have our 4 corners, because we know this one. This one is 0, 50. This one right here is 50, 0. This one right here is 0, 0. So all we need to do is figure out that one. So I think some students may have gotten stuck on this point, but really if we just remember, we're just intersecting the lines right here. We're not intersecting the inequalities because that gives us this entire shaded region. We just want to know this one vertex. So it's the orange line intersect with the purple line. So we could just pretend like these are inequalities to get the actual boundaries of the lines. And we can just do normal pivoting or substitution, whatever you want. The thing that I notice is that since this is 2b and this is 2b, they're already set to eliminate each other, so I can just subtract straight down. So that's what I'm going to do. So I subtract straight down. 5j take away j is 4j, 2b take away b goes away, 250 take away 100 is 150, so 4j is 100, divide both sides by 4, j is 150 over 4, which reduces to 75 over 2. So now we know what the j is. The j is 75 over 2. So how are we going to figure out the b? Well, same deal, just plug it into either one of these equations you want. This one's probably a little bit easier, so I'll replace the j with 75 over 2. This is like the back substitution part. So 75 over 2 plus 2b is equal to 100. Let's move the 75 over by subtracting it. And let's get a common denominator there. So instead of 100, let's do that as 200 over 2. So now they have a common denominator over 2, so I can put this all as one fraction, as 200 minus 75 all over 2. 200 minus 75 is 125, and then you divide by the 2. Let me go back one step there. I did that a little bit fast. So you get 125, then you divide the 2 over, so it becomes a 4 on the bottom instead of a 2. So there's your b coordinate. So now we know the coordinates of that point. It's 75 over 2, comma 125 over 4. Alright, so at this stage we have a pretty good idea of what this looks like. We've got our vertices, we've got our feasible region here. Let's see if GeoGebra agrees with us. So I'm going to see what GeoGebra says and type it in. And aha! pretty much we've got it. So here is our orange juice constraint. Here's our raspberry juice constraint. Notice I've labeled my axes as orangeade and berry fruity, and I put the units on there in gallons, and GeoGebra actually found the intersections for it. It does it in decimals, but it turns out 37.5, that's actually 75 over 2, and 31.25, that's the 125 over 4. So it basically did all the stuff for us. So, well, what's left? Well, we got to figure out which is the optimal vertex. We've got the 4 vertices. Notice that this vertex here and this vertex up here, we don't need those. Right? We don't need to do anything with them. So these are the only 4 vertices that matter for our feasible region. So let's actually figure out which one is our optimal vertex. So don't forget what our thing is, that our objective function. Here's what we're trying to maximize. We're trying to maximize our profit, which is 1/2 j plus 2/5 b. And let's do the easiest point first, which I think we can agree is the origin, 0, 0. So if I just plug in 0, 0, well, I'm going to get out 0. If I don't make any of the orangeade and don't make any of the berry fruity, I'm not going to make any profit at all, so it's 0. Just plug in j equals 0, b equals 0 there. You get out a 0. All right, awesome. Probably the next easiest to do is probably that one. So let's see what we get there. So if you plug in 0 for j and 50 for b, 0 for j, that goes away. 2/5 times the b is now 50. The 50 and the 5 cancel 10. 2 times 10 is 20. So that's how I got that it was 20 so fast. Well, let's go to this corner right here. So let's figure out what the profit we'd make from this. This time it's the b that's 0. So when the b is 0, this part's going to go away. So you just get 1/2 times 50. Well, 1/2 times 50 is 25. So what this is saying is we would make $25 in profit if we made 40 gallons of orangeade and no gallons of berry fruity. We'd make $0 of profit if we made 0 orangeade and 0 berry fruity. If we made 0 orangeade and 50 gallons of berry fruity, we'd make $20 in profit. Now we've just got this last one to figure out what the profit is. And then whatever number is the biggest, that's when we want to take, because we're trying to maximize our profit. So we just have to plug this number into our formula. So it's 1/2 times the j, and I'm writing in fraction form, so I think it'll be easier, so 75 over 2, plus 2/5 times b, and again, that's 2/5 times 125 over 4. So let's see, when you multiply fractions, that's just going to be 75 over 4. Here, I'm just going to cancel a little bit with the 50 and the 125, which is 25. 2 times 25 is 50. So if you have 75 over 4 plus 50 over 4, that is 125 over 4. Well, 125 over 4, I know because we already did the calculation from before, is 31.25. So this is the corner that actually maximizes the profit. Alright, so one advantage of doing this in GeoGebra is we can sort of get the whole 3D aspect of it going. So here's the picture of sort of the way we're used to it right now. So we just kind of graphed out on the XY plane. So we had our raspberry juice coming here, our orange juice coming down like here. Here was our feasible region. But really that's just the shadow of the real feasible region. So let's take a look at this in 3-dimensional space. This is what GeoGebra can do. So I'm going to go ahead and start popping this up into 3-dimensional space. So you can kind of see here, this gray area is the XY plane, right? So this right here, this was the spot, this shadow, that was what we were actually graphing. We were just on the X and Y plane. We were nice and flat, and that's why when I looked straight down, it looked like 2-dimensional. But when I come up and start tilting it, you can realize that, aha, this is really what it's looking like. The z-coordinate is the profit that it makes, right? So it's actually this quadrilateral that's kind of tilted up in 3-dimensional space. What we were looking at, that sort of weird trapezoid shape, that was just the shadow. So in reality, it's up like this. So we want to know what's the high point. And now that we see it this way, we can realize that the high point of this is actually this spot right there. So, shouldn't have double-clicked it. That spot right there. So that's the spot that's above the 37.5, 31.25, and the height of it, just by kind of coincidence, is also 31.25. So that's kind of looking at it graphically 3-dimensionally. So you don't need the 3 dimensions. You can do it in 2 dimensions. Just calculate the profit for each one and figure out which one's the highest. But it's kind of nice to realize what's actually going on there. All right, you don't actually have to do this next part, but I thought it might not be a bad idea to let's double check our constraints to see if what we think works actually does follow the constraints. I mean, it does, but let's just do a little double check. So if you remember, we were going to make 37.5 gallons of orangeade. Well, in the problem, it says that it takes 2.5 quarts of orange juice and 1.5 quarts of raspberry juice in order to make that orangeade. So if it's 2.5 quarts for every single gallon, we'd have to multiply the 37.5 gallons we want to make. And so that's going to say it's going to take 93.75 gallons just of orange juice to make the orangeade, and 1.5 times 37.5, which is 56.25 quarts of raspberry juice. So all of that is what it takes just to make the orangeade. Well, let's take a look at the berry fruity. So remember, we were supposed to be making 31.25 gallons of berry fruity. Well, back in the problem, it said that if you want to make berry fruity, it's 3 quarts of the raspberry juice, and we're making 31.25 gallons of it. So it's 3 times 31.25 altogether just of the raspberry juice. But don't forget, it also takes some orange juice too. So it took 1 quart of orange juice for every gallon we make of berry fruity. So that's 31.25 gallons we're making. So altogether, it's going to take, just from the berry fruity, 31.25 quarts of orange juice and 93.75 quarts of raspberry juice. So do we actually have enough? So let's check it out. So the total amount of orange juice we're going to need is the 93.75 coming from the orangeade and the 31.25 of the orange juice coming from to make the berry fruity. So if you put that together, 93.75 plus 31.25, hey, that does indeed equal 125, and we have enough. Now if we take a look at the total raspberry, 56.25 of the raspberry juice from the orangeade, 93.75 of raspberry juice from the berry fruity, add it up, 56.25 plus 93.75, that is indeed 150, and that matches our constraint. We had the 150 quarts of the raspberry juice, so we're okay there. Or maybe it was gallons, I don't remember now. But, okay. So I just realized that the units do matter. So just as I got this answer, I'm looking at the book, and I realize that it says we have 125 gallons of orange juice on hand. So 125 gallons is actually 125 times 4 quarts. So theoretically, I'd have to redo this problem because my numbers were incorrect. But let's just pretend the problem. So my original hunch at the very start of the video, I said to the person, oh, I think the reason why your numbers didn't match up is because you didn't convert quarts to gallons. And in fact, I now did that exact same thing. So I just made the boo-boo. So I just did it as if everything was in fact in the same units. So really, this is not the correct answer. But all the procedures we did were correct, so I'm going to go ahead and leave it for now, even though technically it's wrong. So at this stage, we would go ahead and, because the question was in a complete sentence, we'd have to answer in a complete sentence. So I would say it like this. So the juice company can make its maximum profit of $31.25 by making 37.5 gallons of orangeade and 31.25 gallons of berry fruity. So that would be your final answer if the units hadn't changed, which they did in the problem. So this answer is actually wrong, because I made the same mistake as the student made that they were saying in class before. So, but anyway, that is the correct technique, and hopefully that helps you understand how to do linear programming problems.